Hello everybody, and welcome back to another dynamics video. Today we're going to be going over rectilinear kinematics of a particle, so let's jump right into it. So just a quick overview of what rectilinear kinematics of a particle means, so you know exactly what we'll be doing in this lesson. So in this case we'll be looking at one dimension rectilinear, so that's just any normal XYZ axis, and we'll just be looking at one of those dimensions. Kinematics means motion only, so no forces, impulse, anything like that. And particle just means a 1D object, so something where we don't care about the motion relative to itself. So let's start with defining the variables. And just a quick note, I use the subscript 0 to denote initial values. So for example, this would be the initial position. And then if it doesn't have that subscript, it's just wherever you are currently or the final position. And then delta means difference. So for example, this delta S here is whatever position you are currently at minus your initial position. So, like we just discussed, the position variable is going to be S. And displacement is the change in position, which is different than here I have distance traveled, which I just listed as a D because I want to describe for you real quick how that works with a picture. So the difference between the displacement and the distance traveled is that the displacement does not take into account how we get from the initial to final position. So if we look at an axis here, and let's say our initial position is over here, and final position is over here, well, no matter how we get from this point to this point, our displacement will always be this length here. But if our actual path traveled looks something like this, where we come past maybe and come back, then the total distance traveled will also include whatever this value happens to be here. So note that the distance does not always equal the displacement. And in this case, our distance is equal to the displacement plus 2 times this value, because you go here and you come back. Now, one last thing to note that is very important is that the displacement is a vector quantity, meaning that it has both magnitude and direction. So in this case, the magnitude is going to be the length of this right here, and the direction is going to be this way. So because it has a direction, that also means you can have positive and negative values for this. So if we denoted this as positive, if your final position was actually somewhere over here, then you would have a negative displacement, which is different than the distance traveled, which is a scalar, meaning it only has magnitude. And this number should always be positive. It's the only real way that it makes sense, because in our example down here, it only represents the length of this total path. So the next variable we're going to talk about here is going to be the velocity, which I use lowercase v. So the instantaneous velocity, which is what we'll be using most of the time, is the time derivative of the position. So essentially it's the change in position over time. And then if you remember from the previous slide, we had the displacement and we had distance, and this is where it really comes into play. So if you want just your average velocity between two positions, then you can use this formula. And if you want your average speed, which takes into account the actual distance traveled, then you'll use this formula here. Also, as we discussed on the previous slide, because the average velocity is using displacement, this will be a vector, and because average speed is using a distance, this will just be a scalar, or only have magnitude. We won't be using this average speed equation very often because often the data that it provides is not the most useful. If we look at the past example where we had a line like this, initial position here, final position here, if your actual path was something like this where you had this extra little bit here, finding the average speed that you were traveling from here to here would take this into account, which doesn't really help that much. It doesn't really provide much useful information, but it's good to know. So the last variable that we're going to look at here is going to be acceleration, for which I use a lowercase a. So the instantaneous acceleration is going to be the derivative of velocity with respect to time, or the change in velocity with respect to time. And if we plug in our velocity equation that we saw on the previous slide, you end up with the second derivative of position with respect to time. And then the average acceleration, similar to average velocity, is going to be change in velocity with respect to time. So on the previous slides, we saw relationships between acceleration, velocity, position, and time, and all the equations were dependent on time. So you'd have to know how long something took to be able to do any kind of calculations. But what if we don't have time? What if we don't know how long something takes? Well, we can get one more useful equation that does not involve time. So let's go ahead and derive that equation now. So from the previous slides, we have this. A is equal to derivative of velocity with respect to time, and velocity is equal to the derivative of position with respect to time. So if we're trying to get rid of this dt in this equation, the best way to do that would be to first solve for dt. So let's do that. dt is equal to dv over a. dt is also equal to ds divided by v. So now that we have dt isolated in each one of these equations, we can just go ahead and set these equal to each other. dv over a is equal to ds over v. So we have a v and a dv here, so those are going to be most useful when paired together. So let's go ahead and start with that. We'll move the v over here and the a over here. So we have v dv is equal to a ds. So this is going to be how we're going to integrate this equation, but most often you will see the ds under the dv, and you'll see this equation written like this: v dv ds. And this here is our fourth equation. Something you also may notice is that in all of our equations we have acceleration equal to something now, with velocity, position, and time in the other cases. So the equation that I like to remember is a combination of all of them. So we have here, we know that a is equal to time derivative of velocity, and we also know that it's equal to the second derivative of position with respect to time. And then if we take our fourth one down here and we throw that in, we know that it's equal to velocity times the derivative of velocity with respect to position. So this is a really good kind of generalized equation to remember, and you should be able to solve any rectilinear kinematics with any of these relationships here. So now you'll notice the title of this slide is Constant Acceleration Solutions. And the reason we say constant acceleration here is because you'll run into a lot of situations where your acceleration will be constant. So instead of trying to deal with solving the integral every time on the equation we saw on the previous slide, which we'll just go ahead and write it up here so that we can see it. A is equal to dv dt equals d squared s dt squared equals v dv ds. So instead of trying to go through every time and solve these integrals, we just go ahead and find the equations for when this is a constant number. So that means when we're integrating it, it won't, that we're assuming this is not a function of anything. So let's start with our first equation. A is equal to dv dt. So first thing we'll do to solve this is we'll go ahead and bring the dt up here and pair that with our constant a, because that will make this very easy to integrate. So a dt. So now we're going to integrate this guy, and for the velocity we're going to go from some initial velocity to a final velocity, and for the time we're just going to go from 0 to whatever the time is. There's not really a use in initial time, is not super useful unless you're doing several different increments of time. Then you may want to use this, but normally you just know, okay, we're looking for these 5 seconds or these 10 seconds. So you can include this to you if you want. I will just be using 0, and this t will represent the total time of whatever duration you are looking at. So continuing, we have a dt. And now, again, this guy is constant. So if you remember from calculus, we can just go ahead and pull him out of the integral. So integrating dv is just going to leave us with a v from v naught to v. And our a is just going to be a times t from 0 to t. So if we go ahead and plug these in, we're going to have v minus v naught is equal to a times t. So a lot of times the way you will see this written is v is equal to v naught plus at, which makes a lot of sense. Your final velocity is whatever your initial velocity was plus whatever your acceleration was times how long you were accelerating. So the next equation we're going to look at is going to be the acceleration is equal to the second derivative of position with respect to time. And instead of doing the double integral here, we're just going to go ahead and look at this guy instead. And what I want you guys to understand most is that the reason we can look at this and integrate either one of these to get the same equation is because they're all really the same equation, just expressed with different variables. So you can, all of them mean the same thing and will give you the exact same solutions, but they just used different variables. So if we remember from our last slide, we ended up with this equation for velocity. V is equal to v naught plus at. So what we're going to do is we're going to go ahead and plug that in over here. We're going to have v naught plus at in for v, and that's going to be equal to ds dt. So now let's go ahead and move the dt over. So we'll have v naught plus at dt is equal to ds. And now let's integrate both of these guys from initial position to final position, wherever you currently are. And from, since we're doing time here, we'll do 0 to t. So now let's go ahead and integrate this guy. So this first part, just v naught, well, the integral of v naught with respect to t is just going to be v naught t, because it's a constant, and then integrating this at term is going to be a times 1/2 t squared. And we're going to take that from 0 to t, and that's just going to be equal to s from s naught to s. So now let's go ahead and plug everything in. Well, if we just plug in t and 0 here, we're just going to end up with this, so no need to plug anything in here really. So we have v naught t plus 1/2 at squared equals s minus s naught. So let's go ahead and bring this up here so we can see it. So we'll have, if we solve for just s, we'll have s is equal to s naught plus v naught t plus 1/2 at squared. And that's going to be our second useful equation. So the last equation we're going to look at here is going to be the acceleration is equal to velocity times dv over ds. So now let's pull this ds over here so that we can integrate this v dv term. We'll have a ds is equal to v dv. And now we will integrate both of these guys from v naught to v and from s naught to s. So remember, this acceleration is a constant term, so we're just going to have a times s from s naught to s, and over here this v is not a constant term because it's v dv, so we're going to get a 1/2 v squared, and again that's going to be from v naught to v. Alright, so let's plug everything in. So a times s minus s naught, plugging in very simply, is equal to 1/2. We can just pull that 1/2 out front because it's just a constant, and we'll have v squared minus v naught squared. So let's solve for this v here because this is not the initial term. So start by moving this 1/2 over and say 2a s minus s naught is equal to v squared minus v naught squared. And finally, solving for that v squared will lead us with this. So we have v squared equals v naught squared plus 2a s minus s naught. So this here is our final equation that we will be deriving. And let me know, if you guys want me to do a little bit more algebra when solving these integrals. As you notice, I am skipping a couple steps just to try to make this a little bit more concise. So now let's look at the lesson summary to review what we just did. So we were looking at rectilinear kinematics of a particle, and we discovered our general governing equation as this right here. So acceleration is equal to the derivative of velocity with respect to time, the second derivative of position with respect to time, and velocity times the derivative of velocity with respect to position. And we discussed that many situations will have constant acceleration, so we went ahead and solved this governing equation assuming this was a constant, and we ended up with three equations. Now, in the next video, we will be doing some example, putting these three equations for use, and just kind of a general note here at the end. The reason we took so much time to derive these equations is because I really want you guys to understand where these are coming from. In general, throughout this whole series, I could just go ahead and kind of skim through and give you the final equations that you need to solve the equations, but you're not really going to understand where things are coming from. And in my experience, if you don't understand that, then you're going to have a lower ceiling of understanding that you can achieve with this in general. That was just what I found from tutoring a lot of people when I was in college. So again, throughout this whole series, we're going to take a lot of time to really dive in deep and understand the math and understand where any of the equations we use come from. So I hope this video was helpful. If you're looking for examples, they will be in the upcoming video, and I hope you all have a great day. Thanks for watching.